everyone, I hope you're all doing well. We're going to start talking about acids and bases today, which is one of my favorite units. It's really cool. That means we've more or less wrapped up talking about organic chemistry, although you'll actually see a little bit of organic chemistry later in today's lesson. But first, I wanted to review a couple of topics that we've actually talked about earlier this school year. Okay, so I've pulled up a slide that has a question for you all. Go ahead and read the question and then answer it. All right, so we want to know which of these solutions is going to have the lowest freezing point, either pure water, 1 molar NaCl, 1 molar C2H6O, or 1 molar BaCl2. If you remember when we talked about colligative properties, we talked about the fact that having anything dissolved in water will lower the freezing point. It makes it harder for the water molecules to form that perfect solid crystal lattice. And so it makes it harder for the water molecules to freeze. So they have to get colder than 0 degrees Celsius in order to freeze. So the answer is definitely not pure water. Pure water would have the highest freezing point of all of these solutions. Now we talked about the fact that the more particles you have dissolved into the water, the more disruption there is to freezing, the harder it is to freeze. And so whichever of these substances has the most concentration of particles dissolved into the water will have the lowest freezing point. So you might think B, C, and D would all have the same freezing point because they all have a 1 molar solution, but actually they don't all have the same freezing point. The solution that has the lowest freezing point is answer choice D, right, BaCl2. The reason for that is because this solution, when BaCl2 dissolves into water, it splits apart into 3 ions, Ba2+, Cl-, and then another Cl- that's separate, right? So a 1 molar solution of barium chloride is really like a 3 molar solution of ions. There's 3 moles of ions per liter of water. NaCl splits apart into Na+ and Cl-, so a 1 molar solution of NaCl, that's kind of like a 2 molar solution of ions, right? Less concentrated than BaCl2. C2H6O, you might think that one would be like the most concentrated, but in fact, this is actually just 1 molar because C2H6O is a covalent molecule. And we know that covalent molecules don't split apart into separate ions when they dissolve in water. They just stay as one big molecule. So when you dissolve C2H6O into water, it's just gonna stay as one big molecule. And so this solution is really 1 mole of particles per liter of water. So we've got 1 mole for answer choice C, we've got 2 moles for answer choice B, 1 mole for answer choice C, and 3 moles for answer choice D per liter of water. So since answer choice D has the most individual particles floating around in the water, it's gonna have the most particles getting in the way of the water molecules, forming that solid crystal lattice. And so it's gonna be the hardest to freeze. So that one's gonna have the lowest freezing point. Let's look at another review question. So take a minute to explain why ionic compounds conduct electricity when they're dissolved in water, but molecular compounds don't. Okay, so we've talked in the past about electricity, right? Electricity is essentially a flow of moving charges. When you dissolve an ionic compound into water, it breaks apart into those charged ions, right? So if it was sodium chloride, it would be Na+ and Cl-, right? If it was calcium nitrate, it would be Ca2+ and then NO3 2-, and separate little NO3 2-. And so when ionic compounds dissolve, they have these charged ions. Those charged ions can now move around freely and carry the electric current with them, right? In contrast, a molecular compound, when you dissolve it into water, it doesn't split apart. It just stays as a neutral molecule. So those neutral molecules are free to move around the water solution, but they don't conduct electricity because they don't have a charge. Good, and we can see in this diagram, right, distilled water, which is actually an example of a molecular compound, right, wouldn't carry a current because it's just got these plain neutral molecules. Solid salt can't conduct electricity either because even though it has charges, those charges can't move. They're trapped into the crystal lattice. But salt water is a perfect conductor of electricity because it has these free-flowing ions that can move easily throughout the solution. So we're actually going to start by testing this experimentally, and then we're going to test a couple of other solutions that contain types of substances that we haven't talked about yet, acids and bases.
Hi everyone! I wanted to test the conductivity of a couple of different substances. So I've kind of hot-wired together this conductivity meter. So I've got a battery right here with a wire connected, and then another wire that trails off into the breadboard right here. This wire is electrically connected to this wire, which plugs in over here, right? This wire now can send electricity through this resistor. Then that can go through this LED, back through the breadboard, and then back to this wire and back to the battery. So right now I have an open circuit, which is why it's not lit. But as soon as I connect these two wires together, you see that the light bulb lights up. If I connect something that conducts electricity between these two wires, the bulb will light up. And if something doesn't conduct electricity, the bulb will stay dark. So let's test a couple of things we actually already know about, and then we'll test some new things. So I brought in as a negative control some purified water, right? So we've talked about the fact that if you have 100% pure water, it doesn't conduct electricity. So let's test this purified water from the grocery store. So I'm gonna go ahead and pop this wire in, and then we'll go ahead and drop in the second wire as well. And what you see is that the bulb actually does light up, but it's pretty dim. So that's telling me that my purified water is conducting electricity, but only a little bit, right? So my purified water is definitely not 100% pure water, right? We know that 100% pure water won't conduct electricity. So this is definitely got something dissolved in it. So however they purified it, they didn't 100% purify it. I'm gonna go ahead and fill the rest of these little espresso cups with some purified water as well, and then we'll try dissolving a couple of other substances in it. So this is our negative control, right? This is how much the bulb is going to light up if the substance doesn't conduct electricity, right? Let's test, I'm going to get the next cup, whoops. My wire is coming. You can see that this is like a little bit, I don't have the correct type of wire, so I just kind of taped it onto the battery. So we've got some more purified water. Now let's try dissolving something that we know should conduct electricity. So I brought in some sea salt, right? I'm gonna dissolve a little bit of this into my water, right? And let's test that now. So you can see the bulb lights up really, really brightly, right? So the salt water conducts electricity really well. We've talked about why that is in the past, right? When you dissolve an ionic compound like salt into water, now the ions can move freely. And because the ions can move freely, we have moving charges, which conducts electricity. Okay, so next I brought in some sugar, right? So sugar is a covalent compound. I'm just going to go ahead and grab some of this, right? And I'm just going to go ahead and sprinkle this in here. I'll dissolve that a little bit. And let's go ahead and test that. So this is not conducting electricity very strongly. This is about the same as my just plain water, right? You can see that the plain water and the sugar water are lighting up the bulb about the same amount. So the sugar didn't help to conduct the electricity at all, right? Compared to the salt water, which conducted the electricity really, really well, right? So sugar does not conduct electricity when dissolved in water, right? And we've talked about the fact that sugar is a covalent molecule, and covalent molecules don't really conduct electricity when they're dissolved in water, because they don't split apart into ions, and so there aren't any charges moving around, right? You might have sugar molecules floating around through the water, but those sugar molecules aren't charged, so they don't conduct electricity. Good, let's test something new. So I brought in a lemon. I'm gonna go ahead and juice it, and we'll test the lemon juice. All right, so here I am juicing my lemon. So my lemon juice now is full of a substance called citric acid. which chemically speaking is similar to hydrochloric acid, HCl. It's not exactly the same thing, but it's pretty similar. Let's go ahead and test my citric acid. Oh wow, so you can see the citric acid lights up the bulb really well. So citric acid is a really, really great conductor of electricity. That's a little bit weird because citric acid is a covalent molecule. And so far, everything we've talked about in the past says that covalent molecules don't conduct electricity when they're dissolved into water. So that's a bit of a mystery. Let's test one more substance. So I brought in some baking soda. Let me go ahead and dissolve a little bit of the baking soda. I'm gonna dissolve a little bit of the baking soda into some water. I'll go ahead and give that a stir. I'm making a little bit of a mess. And let me go ahead and test that one. Oh, so we can see the baking soda also conducts electricity really, really well. So again, here was my plain, supposedly purified water. Oops, this isn't in. Here's my plain, supposedly purified water. And the bulb is really not lighting up very much at all compared to my baking soda, where it lights up really well, or my my lemon juice, which is also lighting up super duper well.
Okay, so we've tested sugar, salt, and acid and seen whether or not they conduct electricity. And what we saw is that sugar does not conduct electricity, as we kind of expected. Salt did conduct electricity as we expected, and then acid, somewhat surprisingly, conducted electricity. We know why sugar doesn't conduct and salt does conduct, right? Salt, when you dissolve it into water, will split apart into those separate positive and negatively charged ions that can then move through the water and carry electricity with them, right? We know that electricity is the flow of moving charges. Something like sugar, when you dissolve sugar into water, the sugar stays as one big molecule because it is a molecular compound rather than ionic. So the C12H22O11 just all stays bonded together. And so what you end up with is you end up with a whole bunch of neutral molecules. The molecules can move freely, but they're neutral, so there are no moving charges, right? And so sugar does not conduct electricity because it has no moving charges. Salt does conduct electricity because it has moving ions when you dissolve it into water, right? Solid salt does not conduct electricity because even though it has the charges, they're not free to move. Okay, now acid conducted electricity. That means that the acid must have moving charges, which is weird because this is a covalent molecule, right? What we've talked about in the past is that ionic compounds break apart into charges when they're dissolved in water, and covalent molecules don't. And it turns out that was actually an oversimplification. It's true most of the time, but not all of the time. Acids are our exception to that rule. So an acid is a compound that's normally covalent. It's a molecular compound, but when you dissolve it into water, it will still split apart into separate charges, similar to an ionic compound. So if you dissolve HCl into water, what you're going to end up with is you're going to end up with H plus ions and Cl minus ions that are separate from each other. The covalent bonds between H and Cl will actually break when it's dissolved into water, and the H plus will move around separately from the Cl minus. So an acid is an example of a covalent compound that conducts electricity. It's a covalent compound that conducts electricity when dissolved in water because it splits apart into these different ions, even though it's not normally an ionic compound, right? HCl, that's considered a molecular compound with a covalent bond because H and Cl are both nonmetals. However, hydrogen is sort of a funky element. Hydrogen is a nonmetal, but it's pretty close to being a metal. It has some very metallic properties. It has a really low electronegativity compared to all of the other nonmetals. And so it has a really weak pull on its electrons. And we know it's all the way over in group 1, right, where the rest of the group is all metals. So even though hydrogen is a non-metal, it can sometimes kind of act almost like a metal, right? In NaCl, you split into Na plus and Cl minus because the electronegativities are so different that chlorine just rips all the electrons off of sodium. HCl, if it's in a gas state, it'll be bonded covalently. But if you dissolve it into water, the chlorine's pull on the electrons is strong enough that it will pull all the electrons away from hydrogen. And the H plus and the Cl minus will actually get separated from each other. That's a characteristic of all acids. Acids all conduct electricity because they all lose H plus when they're dissolved into water. Let's look at another example of an acid. So another example of an acid would be vinegar, which the main component of vinegar is acetic acid, C2H3O2H, which you can already tell there's something funky going on based on the way we write the chemical formula, right? If we were to draw out the structure for this, it would be carbon bonded to carbon. This carbon has 3 hydrogens. This carbon has 2 hydrogens. Nope, that's not true. This carbon has no hydrogens. This carbon's double bonded to oxygen, single bonded to oxygen, single bonded to hydrogen. Right? So this is the chemical structure for vinegar. And we can see, oh, it's got to be an acid because this has the organic acid functional group from your table, from your reference table. So if we were to name this using our organic chemistry naming rules, this would actually be, it's got 2 carbons, this would be F, so this would be ethanoic acid, right? So this one molecule has a whole bunch of different names. The technical name would be ethanoic acid. This molecule is an acid because it can lose hydrogen. In particular, it can lose this hydrogen that's bonded to this oxygen, right? Hydrogen and oxygen have very different electronegativities, and so in some circumstances, and in particular, if you have this whole functional group where you have carbon double bonded to oxygen, single bonded to oxygen, single bonded to hydrogen, the functional group is able to lose a hydrogen. So when you dissolve this molecule into water, this hydrogen is going to pop off. And what you're going to end up with is you're going to end up with a separate CH3COO, which if you remember from your polyatomic ions, that's acetate, and then H plus separate. So you're going to end up with CH3, C, double bond to oxygen, single bond to oxygen. You're going to end up with this, and then a separate H plus floating around. So acids in general conduct electricity when dissolved in water because every acid, when you dissolve it into water, loses H plus. So acids characteristically lose H plus when dissolved into water. That's one way to actually define what it means to be an acid. Okay, so fun fact, anything that conducts electricity when dissolved in water is called an electrolyte. You might have heard that word in like commercials for sports drinks like Gatorade. So they'll be like, oh yes, it replenishes your electrolytes, which is a fancy way of saying it replenishes like stuff dissolved into water. So this is anything that conducts electricity when it's dissolved into water. So that would include any acid, any base, and any ionic compound. All of those are electrolytes. So an electrolyte is just something that conducts electricity when dissolved in water. So an example of an electrolyte would be any acid, any base, or any ionic compound. But for example, sugar and most other covalent compounds, other than the ones that are acids, would not be an electrolyte, because sugar does not conduct electricity when it's dissolved into water. So now you know what that word means when you see it in Gatorade commercials. Okay, so we saw that acids lose H plus when they're dissolved in water, and so because of that, they conduct electricity. Cool. Bases, one example of a base would be baking soda, which we tested. So bases also conduct electricity. If you take a look at your reference table, you can actually look up the formulas of a couple of common bases. So if you look at your reference table, you'll see sodium hydroxide, which is a common base, potassium hydroxide, calcium hydroxide, right? You'll notice that a lot of those bases actually are ionic compounds, and all ionic compounds conduct electricity. But in particular, what those ionic compounds have in common is that they all have hydroxide. So what makes something a base rather than just a normal ionic compound is that a base loses OH minus when dissolved in water. Both acids and bases conduct electricity because they both split into ions when they're dissolved into water, even if it's something that started out as a covalent molecule like HCl did. Okay, so since they both conduct electricity, we need some other way to distinguish acids from bases. One of the most common methods is actually through taste. So I've got my lemon right here. Let's go ahead and taste this. And that's actually pretty good. I like lemon juice, but it's quite sour, right? But you know, one acid isn't enough to prove that all acids are sour. Maybe that's just lemon juice. So I brought in a second acid, right? This is vinegar, which I'm going to go ahead and crack open. Oh, that's disgusting. Oh, that's really gross, but also very sour. So acids are characteristically very sour. Okay, what about bases? Okay, let me go ahead and try my baking soda water, which is a base for comparison. Yeah. So that's also pretty gross, not as gross. That one's super, it's not sour, it's like very bitter. Okay, so let's try one more base for comparison. So I brought in some Clorox Tilex spray, which contains bleach, which is a base. So let's go ahead and test that one out and we'll see how that tastes. No, I'm kidding. Don't drink bleach at home. Bleach is super poisonous. But if somehow one were to drink it and survive to live the tale, bases are characteristically very bitter tasting. So acids characteristically taste sour. Bases characteristically taste very bitter. Okay, now as we can see from bleach, you don't always have the chance to taste every random chemical that you come across. In fact, that's a very bad idea. And so we need some sort of other way to tell the difference between acids and bases other than like drinking them. Right? Well, the most common method is something called pH. So let's check out the pHs of our acids and our bases.
All right, so if you don't want to drink your mystery chemicals, then you can actually tell if something's an acid or a base using pH paper like this. So pH paper is basically these little strips of paper that have been soaked in this substance called an indicator that changes color based on the pH. So you can kind of dip the paper in and then match it to the colors on here to figure out what the pH is. So let's go ahead and test a bunch of our different substances, and we'll see what pH they have, and we can figure out if they're acids or bases. So water, let's go ahead and test water. So here's our water. The strip didn't really change color much at all, which if we actually match it to the strip, looks like a pH of about 5 or so. Water is normally neutral, right? It normally has a pH of 7. So I suspect that my pH paper is actually a little bit old. And so we'll have to use this as our control going forward, right? So a neutral solution is basically looking kind of like this. Let's go ahead and test the next couple substances. All right, so I've got sugar water, which you can see looks just exactly the same as the original water. So sugar water is also essentially neutral. We've got our salt water. Again, that looks pretty neutral. We've got lemon juice. Ooh, and you can see there's a big color change there. So if we compare this to our colors here, it looks like the lemon juice has a pH of somewhere in the red color range, right? So maybe about 2, it looks like to me, maybe 1 or 2, right? So our lemon juice has a very, very low pH of around 1 or 2. Let's check our baking soda, which we know is a base. Ooh, and we've got this nice green color. So our baking soda, it looks like has a pH of about 8. Right. Let's check another acid, right? So we don't want to check just one. So let's test our vinegar. Again, we're getting this red color. The vinegar looks like it has a pH of probably about 2. And then lastly, let's test some bleach, which I didn't go ahead and pour out because it's in this nice little spray bottle. So I'm just gonna go ahead and spray some of this right onto the strip right here. And you can see this has turned this really dark blue color. Aside, it's also like bubbling. But so this has a pH of maybe like 10 or 11, right? And so what we see is that the acids have a pH that's very low, right? Around 1 or 2. The water, sugar water, and salt water, which are all essentially neutral, have a pH that's pretty close to 7. And then our bases have a much higher pH, around the 8 to 11 range. So in general, a neutral solution is going to have a pH of about 7. An acid is going to have a pH in the 1 to 6 range, and a base will have a pH in the 8 to 12 range.
Okay, so as you can see, acids characteristically have a low pH, a pH that's less than 7. Bases characteristically have a high pH, a pH that's greater than 7. And then something that has the pH that's exactly equal to 7, we would call neutral. So something like water, where the pH equals 7, that would be considered neutral, neither an acid nor a base. Awesome. I hope this has been a helpful introduction in the difference between acids and bases. And I look forward to talking more about this with you next time. All right, I hope that was interesting. On Friday, we're actually going to be doing a digital experiment with acids and bases. And then we're going to do a real experiment next week using purple cabbage. So if you have a chance to have your parents or someone else pick up purple cabbage for you, we actually only need a couple leaves. So you could even just grab a couple leaves. You'll be able to do the experiment at home. If you're not able to get a cabbage, that's fine. You can follow along with the video. I'm going to do the experiment and you can follow along with me. But it'll be a lot more fun if you actually do it yourself. And you can see my purple cabbage was only $1.88 for the entire cabbage. It's pretty cheap. If you have a chance to get one, definitely do it because it'll be a lot more fun to do the experiment for real. All right, I will see you next time.